record. There it is. Okay. So yeah, so you're looking at this sheet right here. Oh, there's my conversion sheet. You want to look at this side by side and ask yourself, what type of unit is it? For the most part, you have three main classes of measurements, and then the last one is going to be time, the main ones that you guys are going to be looking at, right? So you ask yourself, is this conversion here, or are these measurements lengths? Are they mass, or are they volume or time? It's obviously not time. So then if you look at it, you see how there is this kilometers right here. So this is most likely a length conversion. So the section you want to look at is length. Can you find a conversion that has both this top one, kilometers and miles, in it? So you want to go over here and see kilometers. This M is not miles, it's meters. I look all the way down here. I don't see it. I see a mile and I see a kilometer. So I'm going to use this conversion right here in a direct conversion. So 5.78 kilometers. You use your conversion brackets. Remember, the units you write up here have to match diagonally with the units you write on the bottom. So the conversion I'm going to use here is I write it with pen. 1 mile equal 1.609 kilometers. Okay, that's the conversion I picked from the conversion table. Oh, let me scoot this over. I feel like I never have enough space right there. Okay, so I'm going to use my conversion that I wrote, but remember, in the conversion, the kilometer part has to match the kilometer part diagonally. So I'm going to write this number right here and its unit on the bottom because they have the kilometer unit. So it'll be 1.609 kilometers. Then on top, I will put 1 mile. Okay, so kilometer will cancel out with this kilometer, and then it will give me my answer in the desired unit. Mathematically, I'll write 5.78, and then I will multiply by all the top numbers, and then divide by all the bottom numbers. And when I work this out, I actually get my answer in the desired unit, the unit that did not cancel out. So 5.78 times 1 divided by 1.609, and I get my answer as 3.59 miles. Okay, so now I'm going to do something else. I'm actually going to do a density this time because you see down the road we'll be using density as a conversion. So I'm going to do a density. Density is weight over volume, right? So I'm going to pick a weight, a different kind of weight. Let me pick pounds. So I'll say 1.4 pounds over, I'll say centimeter cubed. Okay, so this is our starting point. We're going from pounds over centimeter cubed. Then we're converting this to, well, let's say grains.
Dr. White,
The what?
excuse me. Can you complete the first one, please, for me?
This first one?
Yeah, the kilometer and mile.
Oh, this is the answer, 3.59 miles. Yeah, I multiplied the 5.78 times 1 divided by 1.609.
Oh, okay.
Did you get a different answer?
Yes. I did multiply 5.78
Mm-hmm.
to 1.609. Yeah,
Oh, yeah, you can't multiply because it's in the top and bottom. The ones that are on top are multiplied. The ones that are on the bottom have to be divided.
yeah.
So
Okay.
I see. If you put it in your calculator like this, if you say 5.78 times 1, and then, well, yeah, since this is the only number you have to divide. Does that make sense?
Yes.
All the top ones you multiply, all the bottom ones you divide. It makes it so much easier if you do it that way.
No, you know what I did?
Uh-huh.
I put 1 mile in the bottom and 1.609 in the top. That's why.
Oh, you flipped it. Yeah, the way these work, the only way it works, these units have to be diagonally across. They have to match. So if you put mile on the bottom, you won't get the answer right because your answer will have a different unit. If you flip this, so the way you're doing it, if you flip it, oh, this is not going away. Like that, and you put 1 mile on the bottom and 1.609 kilometers on top. I'm not going to do the math. I'm just going to do the units. This will not cancel out with that. The kilometers and miles won't cancel out. So what will happen? This will remain. It will still be there. And then your answer will be in the wrong unit. Kilometer times kilometer will multiply with each other, and you will get kilometer squared over mile. This is not right. So if the unit is not right, the number will definitely be wrong. We need only mile,
Okay.
right?
Are you gonna show us
Yeah.
how to make the answer, if it's like a really big answer, a really small number, like into scientific notation?
Oh, I can do that. I can add it to the list. Yeah, the good thing about this here, you tell me what to do and I do it. So I'll add that scientific notation. Scientific notation. Okay. Yeah, so large number to small number, right? And then do you also mean significant figure, like rounding up and down? I'll do
Yes.
that one too. Rounding up and down. Okay. So let me do this other conversion right here. This one here is the unit. So remember, in the conversion, I did a video explaining what the starting point is. I did all that. So that's in my old videos. You can go ahead and watch that. But this is kind of like a puzzle, right? In the conversion. The unit they give you first, that's where you start. It tells you which one of these conversions to pick, which one to pick first. And then the unit where you end. So let me do something a little bit simpler before I come to this one here. I'll finish this question and then I'll write something else. I'll do a much simpler one first before I do this. So I have grains, and then down here for my volume, let me pick liters, grains per liter. Okay. Okay. So let me cut this and put this down. I'll come to this later on because this is more complex. So right now, let me do another one here. This one will be 1.115. And let's say this is millimeters. And this time we're going to meters. Okay. So if we're going from millimeters to meters, once again, you want to find in this category here, in this category, is this length? Where's my mouse? There. Is this length? Is it mass? Is it volume? So try to find where, if you know this already, that meter is a length, that's good. If you don't, try to find millimeters in one of these places or meters. So you look over here, you see meters, meters. Okay. See if you can find an equality or conversion factor that has millimeters and meters together in one conversion. Okay. So I see meters here. I see centimeters and I see millimeters. Okay. So the way this is written, all we need is the first part and this last part. So we need 1 meter equal 1000 millimeters. So I'm going to write that down. My conversion factor is 1 meter equal 1000 millimeter. That's how I'm going to use this from here. I don't need the centimeter one. I just need meters and 1000 millimeters. Okay. And this one has both the wanted, that one there, and the given, that one there. Okay. You see that it matches that. So after you have the conversion picked, you want to write down the first given number, 1.115 millimeters, right? Then you use your conversion bracket like this. And with the conversion bracket, then remember, whatever you have up here, you have to have the same unit down here. So when I was still learning this, once I figured out the units have to match, I'll just write down here millimeters before I even knew what the number was. Because I knew no matter what it was, it has to be millimeters, right? For this to work. Now I
Yeah.
go looking for the number. Oh, look, I only have one number to use. And there is 1,000 millimeters here and 1 meter. So now I can put the thousand down here because they go together. Thousand. I can put the 1 meter here. Oh, look, it works, right? Because the millimeter cancels out with a millimeter, and then my unit will be meters. If my unit is right, now I can start doing the work. There's no point in you doing the math if the unit is wrong, because if the unit is wrong, the math will definitely be wrong. The unit is right, so now let's see. For the math, I'm taking 1.115 divided by 1,000, like that. So 1.115 divided by 1,000, I get 0.001115. 0.001115. That's a small number, but I want to make sure I got all the numbers right. And that's what I get from my answer. Because my unit was right, my answer will be right. 315, right? And so I put this number right there. Any questions about that second one? Let me write this a little lower. Okay. So Victoria, um, was the
I'm
homework
sorry.
okay?
I'm sorry, Dr. White.
Yes.
Should I write this answer in scientific notation?
You can do it either way. So this is what Victoria was asking me about. You can write it like this, or you can write it as if you're gonna do scientific notation, then remember you want to move the decimal 1, 2, 3. Okay? 3 to the
Mm-hmm.
right. If you write it like that, then you're gonna write 1.115 times
Right.
10 power negative 3 because you move the decimal to the right.
Yeah.
And then meters. So either one is right. In your homework, so that's what I was about to ask you about the homework. In your homework, um, either format should be okay. The issue with the homework, because it's a computer, sometimes it only has one correct format. So either question, either way you write the answer should be correct, but it may want you to put it in scientific notation. And if that's the case, then write your answer in scientific notation. On the exam, your exam is mostly multiple choice, so pick the right answer.
Okay.
Okay. So, Victoria, since you are ahead, is there any question in the homework that you struggle with or you want to go over again? We can do that too, if you can
Okay.
think of something. Or
Dr.
YouTube
White, I I don't know the last one actually.
in the homework.
Yes, the lab homework.
Okay, in chapter 3.
Yeah, the part. The,
Okay, so let me write it down as a list of things to go over. Let me do this conversion first, and then we'll go over that homework.
okay.
Okay.
Thank you.
So here, and then I haven't forgotten, I'm taking notes so I don't forget. I do have scientific notation. Let me finish the dimension analysis and then we'll do the homework. And if we haven't done a lot of scientific notations, then we'll go over that again. So let's do this one here, the one with a unit over a unit to give you another unit over a unit. So here, just to help you visually see, we'll look at the top unit here, the one in yellow, and then the other one in yellow. Hopefully you can see that color. We're going from pounds to grains. I picked a weird number, a weird conversion, right? From pound to grain. Pound is a mass. So I go over here and I say, where is the mass? I'm looking for pound. Pound should be somewhere here. I see pound here. Oops. I see pound here. I see pound here, and then there's so many pounds here. And then it says you have to go to grains. And I see grain here, and the grain goes with 1 gram. So since I only see one grain conversion, I'll actually start with that. I will write 1 gram equal 15, I think that's 4.43 grains. Okay, I picked the one conversion I found here that has grains. So this is showing me I want to go directly from pounds to grains, but I'm not going directly from pounds to grains. I'm going from grams to grains. Do I have one from pound to grams? Let me see. There's pound to ounce, pound to ton, pound to grams. Oh, there's one here. So I'm going to go from pound to grams, then from grams to grain. Okay? So here I'm going to write 1 pound equal 454 grams. Do you see what I just did? The ideal plan is to go directly from pounds to grain, but there is no direct conversion here. I just looked, there's no direct conversion. So you can go indirectly from pound to grain. That will be your first conversion. Your second conversion will be going from grams to grain. Okay, so it's like a detour. Instead of going to a destination directly, you go to a different destination and then you go to the desired destination. It's a little longer, but it gets you there based on the conversions we have. Okay, that will be my top conversion. So let me go ahead and get one for the bottom conversion. For my bottom conversion, I use the same color. Can I go from centimeter cube to liters? That's volume. So I'm going to go over here and scroll down. I'm looking for a centimeter cube. Oh, there's centimeter cube. And on the right is liters. So there's a conversion. 1,000 centimeter cube goes to 1 liter. Okay? You see that? Let me move my mouse. So for centimeter cube to liters, I have a direct conversion. There's no in-between conversion. So just one conversion. So I draw my brackets, once again, 1.4 pounds per centimeter cube. I draw my brackets here so I can make sure I have enough space. Now, one thing, this number here, the 1.4 goes with pounds, but right now I have no number that goes with centimeter cube, so I'm going to put 1 on the bottom. It doesn't change the top number or the value. Anything divided by 1 is the same number, so that's it. I draw my conversion bracket. So now I'm going to ask you, you get to pick. Do you want me to convert the top part, the pound, or the centimeter cube? You can start either one. It doesn't matter. Your answer will be the same.
I think centimeter cube in the top.
Okay, we'll start with centimeter cube, okay? Because centimeter cube is on the bottom, you have to place, another centimeter cube unit on the top. The only way to get rid of centimeter cube is by writing another centimeter cube opposite, diagonally opposite from where it is right now. Okay, so you see me do this. I will write a centimeter cube on top right here. Now I have to go find a number or conversion that has centimeter cube in it. From the 3 I wrote here, only one has centimeter cube. That's the 1,000. Right? So I'm using this. 1,000 goes with 1 liter. That's done. Centimeter cube cancel, centimeter cube cancel. I'm left with liter on the bottom. This bottom part here, I'm done with that conversion. Next one, I have to get rid of pounds. Since I'm trying to get rid of pounds, pounds is now on the top, right? I have to get a pounds on the bottom, diagonally across, like that. That's the only way to get rid of pounds. Any question about that? If you're trying to get rid of a unit, bring the same unit on the opposite side, like diagonally opposite. That's how this bracket works. So I want to remove the arrow so it's not distracting. So I'm looking for a number that has pounds in it. Oh, I didn't write it fully here. It's supposed to be 1 pound. 1 pound is 454 grams. So I have to use this one here, right? Because it's 1 pound, 454 grams. I just use this. Pound and pound cancel out. My top unit now says just G for grams. They say the top unit has to say grains. So I'm not done. I have to do one more conversion. I have to get rid of G and bring in grains. My last conversion is right here. Since I have G on top, I want to get rid of G. I put G on the bottom. When I look over here, I have 1G that goes with 15.43 grains, right? G and G cancel out. Now, I'm not even doing math yet. I don't want to waste my time doing math. If my units don't work out, the math is going to be wrong. I have grains on top, like they said, have grains on top, and then have liters on the bottom. Let me check. I have liters on the bottom. So my math will be correct because my units are correct. When I work everything out, I'll have grains on top and liters on the bottom, just like they said. So now my math, I have to multiply everything on top. 1.4 times 1,000 times 454 times 15.43. Okay, now you can divide by the bottom numbers. Divide by 1, divide by 1, divide by 1, divide by 1. It will be the same answer, but yeah. So let me put this in my calculator. 1.4 times 1,000 times 454 times 15.43 divided by 1, divided by 1, divided by 1, divided by 1. Shouldn't change the answer. Oh, I get a big number. I get 9807308. Okay, so here is where, Victoria, you asked me this question. Okay, 9807308. We're going to take a big number, right, and write it in, we're going to round this up. So we're going to round up based on scientific note, based on significant figures. And then we can choose to write our answer also in scientific notation, okay? So my given number, this original given number, this is two significant figures. So my answer has to be two significant figures. So only two numbers here are going to remain. No, I shouldn't say two. Yeah, only two numbers are going to remain. For the remaining numbers, they'll be replaced with 0. So this first number here, this second number here, this will remain. All the remaining numbers will be replaced with 0. Okay?
Okay.
So 9, 8,
Point
0, 0, 0, 0.
no.
Wait, 1, 2, 3, 4, 5. 0. Okay. I thought I was writing too many zeros. 1, 2, 3, 4, 5. Yeah, each number gets replaced with 0. If this number here, if the third number was bigger than, if it was 5 or bigger, I will round it up, but it's not. So all the remaining numbers get replaced with 0. I can write my number like this, or I can change it to scientific notation. And to do that, let me write this number here, 9, 8, and 5 zeros. 1, 2, 3, 4, 5. So with this one here, with 5 zeros, I want to write this scientifically. There's no decimal right now. So I add my own to the right, and then I move it to the left. 1, 2, 3, 4, 5, 6. I have to move it 6 times to get one non-zero to the left. So I write 9.8 I can drop off the remaining zero, right? Times 10 power. I move 6 spaces.
6.
6. And leave it as is. Don't put a negative because this number is smaller than the original number. So just like that. 9.8 times 10 power 6. And that's my answer. So you see, I made sure the units were correct before I did any math. Before I took math classes before chemistry, so I was doing the math first and then doing the units and realizing I was wrong. Actually, I was leaving the units out and I was getting in trouble for that. So I learned later on chemistry is not math. Chemistry, we use math, but we care about the units. So you have to put the units. If the units don't work, don't even waste your time with the math. Okay. So are we good here?
Yes.
Okay. So now let's move to the, I move this down. See, I have a lot of windows open. Let's move to the homework. Let me exit preview. I'll go direct link here. And then after we work this, we'll also work some chapter 4 questions. That's what's coming next to make sure that we're helping. Assignments. Okay. So you said it was chapter 3, right? Towards the end. Question 11. This one?
No, I'm sorry. I'm talking about the lab questions.
Oh, lab. Okay. Lab. Well, since we've done this, you can do the lab question, right? The last one?
No, the D one, the last.
Yes. The whole point of us do, you want me to do the exact one?
Yes, please.
The whole point of us doing this was for you to do that one. Okay, let
Okay,
me go
no,
find.
no, Doctor Boy. I will try by myself. If I
Uh-huh.
have question, I send an email to you. Okay?
Okay. I mean, let me see. Let me hold on just a second. I don't even have that question with me right now. We can work on it together since you're here right now. It would be a lot easier. Let me see. So course assignment. Do you have the question so you can read it out to me? It'll be easier. I
Yeah,
know.
it's 30 centimeter to second. Um,
Okay. And you're
yeah,
converting
30
to.
centimeter divided second to miles divided to hour.
Okay. So the difference there, the difference with this, which I mentioned in my discussion last week, is this conversion chart here does not have time. See, it has length, mass, volume, but there's no time, right? And that's the challenge. They left out time because they assume you know. So I'll just say here, with time, you want to know that 1 week is equal to 7 days. 1 day is 24 hours. 1 hour is 60 minutes. 1 minute is 60 seconds, right? At least if you know that at your level of chemistry, I think that's pretty good. Okay, so once again, break up the top part from the bottom part. The top part is lengths, right? Centimeters to miles. So you want to ask, let me erase this here because I wrote it right there. You want to ask yourself, what kind of measurement is this? And can you get a conversion that goes directly from centimeters to miles? So let's go to our length conversion. I see centimeters here, but it's to meters and millimeters. So no, centimeters to millimeters. Let me move on. Maybe I should look for miles. Miles to kilometers. I see miles to kilometers again, miles to feet. So I'm not seeing a direct one, right? So let's do this. You can start from centimeters if you want, or you can start from miles. It doesn't matter. I will start from centimeters and I want to go to meters. Once again, there's so many different ways to do this, right? You can also do centimeters to feet. I'm looking at that. Actually, let me do that one. Let me go from centimeters to feet and then feet to miles. That works. So what I mean, before I pick my conversion, my plan is to go from centimeters to feet. Okay. I'll use this conversion right here. I saw it. This. Hopefully you can see on the right. 1 foot is 30.48 centimeters. And then from feet up here, I can go to miles. You see that? 1 mile. So from feet, I can go directly to miles. That would be my second conversion. So for my top conversion, I'm going to do this first, then I'll do this second. As far as our time conversions are concerned, I only need the last two of these. So I'm going to erase that.
Okay, I have a question. Can
Yes.
I directly convert miles to centimeters
Using this chart, no.
if I Google it?
But it takes away from you learning this. And when people do that, they get it wrong. Most people who I see who Google it, they get it wrong because they don't have a way to check their answer.
Yeah, okay.
Right. So when I'm showing it to you, I'm not going to show you Google way because my goal is to teach you how to do this. Because here's the thing: can you Google it? Yes. Will you get it right? Some people get it wrong. Some people get it right. But there conversions we're doing later on that require you to know how to use this. So
Oh,
if you
okay.
Google it now, then later on when we're moving on to other things, you're still struggling with this. You get what I'm saying? So
Oh,
it's
yeah.
it's not helping you, right? I know this one here is tedious, but in the end, it once you figure it out, it makes the other stuff we do a lot easier. Not
I
easy,
got it.
just a little easier.
Okay,
Okay,
I
so let me,
got
let
it.
me let me write the centimeter to foot. Right here, 1 foot FT equals 30.48 centimeters, right? So I'm writing this one here. Then I use 1 mile. The issue with online is if you don't know what you're doing, you can't check your work because you're just trusting a website. And sometimes what they write is not true for what you're doing. And so people are surprised. Sometimes, one time this guy was getting 90s in all his assignments. Then I gave him one assignment and he Googled everything and he got a 70. And he asked me, why did I do very badly? I said, because your answers were not right for what I was asking you. You just Googled, so you weren't careful. And so from then on, he stopped Googling his answers and he went back to getting 90s. So it's little things like that. I think I got feet, centimeter, miles. I'll write this as MI. So yeah, for some people it works, for some people it doesn't. I think I got my conversion here. From seconds, I'll go from seconds to minutes, minute to hour, right? I don't have a second to hour direct conversion. So here I'll do this one first and then the second one. So for this conversion, I need all these four conversions. The top two are distance or length conversion. The bottom two are time. Okay. So I write my equation like before, 30 centimeters per second. I'll put one here because I like to have a number in the unit. Then on top, let's see. Oh, which one do you want to start with? You want to do seconds first or centimeter?
Can we do centimeter?
Okay, centimeter. So the centimeter, then centimeter has to be on the bottom, right? So that means I have to use this top number here. I have to use 30.48 centimeter and then 1 foot. So centimeter and centimeter cancel out. I just use this. Then now I have foot. So I pick my next conversion that has foot in it. That's this right here. This has to be FT, foot. 5280, and then 1 mile. Okay, so for feet cancel out, and then we have mile on top. Oh, so I'm done with my top part, my top conversion, right? So I got to mile on top. I'm done with that part. Now the only thing I have left, I have to get rid of S and bring in H. So to get rid of S, S is now on the bottom. I have to bring in an S on top. So that means I have to use this number down here with
60.
60 seconds on top, 1 minute on the bottom. So seconds cancel out. I'm not done yet. I'm still just right here, minute. I have to do one more conversion and bring minute on top and bring hour on the bottom. So when I was a student and I was learning this, I write minute up here and I panic. I'm like, no. And I remember, no, they want hour on the bottom. Don't worry about it. If you set this up correctly, it works out. So now when I work it out, I'm less anxious. But in the beginning, I didn't know the process very well. So it took me a while to realize if you set it up correctly, it works out. You don't have to panic. So 60 goes with minutes, and then 1 hour. There. So minute and minute cancel out. Before I do any of my math, I'm going to highlight my the desired. I have to have miles on top. I have miles on top that did not cancel out, right? I have to have bottom. I have hour on the bottom. Everything else canceled out. Okay. So when I do my math, I will have miles on top and then over hours on the bottom. I don't have a lot of room here, so I write on the bottom here, miles over hour.
Okay.
So now I can do my math. 30 times 1 times 1. Multiply all the top numbers times 60 times 60. Divide all the bottom numbers. Divide by 1. Divide by 30.48. Divide by 5280. Divide by 1. Divide by 1. I'm saying write it this way, put it this way in your calculator. If you say divide by multiply, your calculator will do it wrong. People miss it for that reason too. So 30 times 1 times 1 times 60 times 60. Oh, divide by, okay, hold on. Divide by 1, divide by 30.48, divide by 5280, divide by 1, divide by 1. Let me see. Okay, I get 0.6710, whatever. So if you write here, I usually get 0.671. I know I didn't write the book, but they should have put like 30.0 here. So I accept 0.671, I accept zero point 0.7. If I see the work like this, I accept zero point 0.7, I accept 0.671 or anything like that. I've gotten very strange numbers from the internet from people who've done this question. Because with this one here, you can check your work. If you're using stuff online, it's really difficult to check your work when you don't design that program, right?
Yes. And we can ignore all the ones, right?
Yeah, you can ignore all the ones. You can just
Yes.
make your math a lot easier and just do 30 times 60 times 60 divided by 30.48 divided by 5280. Right. We can do just that. It'll make it so much easier.
Thank you so much.
You're welcome. Okay, so I have a list here. I've done scientific notation. We've done some rounding up. So what do we want to do next? A little bit of chapter 4. Okay, so let's see. So we don't have a lot of conversions in the next chapter. I think we do have a temperature conversion for the next chapter, chapter 4. Since I'm not doing a regular lecture, I'm just going to be going over some questions. I'll go over how to rearrange the equation. For this part, I'll say you want to know the temperature conversions, these ones right here like this. So for chapter 4, conversions, you want to make sure you know the pressure conversions, these right here. I don't know how big this is. How do I? Oh, there. Trying to figure out how to use this. Yeah. With the conversions for chapter 4, make sure you know the conversions like 101.325 kilopascals. Know that equal to 1 atmosphere. So it's similar to what we're doing right now, but chapter 4 is about gases. So you want to know this conversion here. You want to know 1 atmosphere equals 760 millimeters of mercury. You want to know 1 atmosphere is also equal to 760 torr. So in chapter 4, the chapter where you're talking about gases, these are the conversions that are very important. So based on that, 1 torr is equal to 1 millimeter of mercury. And then there was one more conversion I saw. Oh, 1 atmosphere is equal to 14.7 psi. They have it written here as pound per inches, but that's the same thing.
What
So
is?
when you have this
I have a
conversion
question.
here,
Sorry.
yes,
How do you say the second one? mmHg. What is that measurement?
millimeters of mercury. So with this one here, it's actually you're measuring the height of mercury in a column. So it's just millimeters, millimeters of mercury. It's the height of mercury in millimeters. You know how the old school thermometer that they used to use in the hospital or even in school had mercury in it? So the way they use that same setup to measure the pressure. And the way they measure the pressure is by measuring how high up the mercury goes in the column. Okay? So what I'm going to do here, since you asked me that question, let me go over this part over here real briefly. Oh, in your class, this is available. Let me make this available in this class here. I have to make sure the dates are good, but essentially, I won't go into all the lecture and stuff because, as I said, that video is already posted anyway. I want to talk more about the questions and how to work out the questions. I'm seeing the videos are all over here. Hold on. There it is. Yeah, so this chapter here is about gases. And in the gases, it tells you what we're going to be going over. The first thing it goes over here is the behavior of gases. You can look at that behavior of gases later on. The thing I want to talk about here is the conversion with the gases, the math part. So please watch the video so when we meet the next time, we can talk about the gas pressure. Right, so we're talking about this here. So in the lab, the pressure of the gas was measured by using this device here. Hopefully you can see my screen. With a device, this test tube here, it looks like a test tube, but it's really big. This was filled with mercury, liquid mercury. It looks like a liquid, but it's actually a metal. It was filled with mercury, and it was full, all the way full, and then it was tipped over with full of mercury. And when it was tipped over, the mercury was allowed to pour out, like to kind of drain out of this tip until it stopped draining out. And so the scientist, Torricelli, who was doing this experiment, noticed that every time he had this test tube device full of mercury, and if he tipped it over, all of the mercury did not come out. Some of the mercury came out, and what stopped the mercury from coming out was what we call atmospheric pressure. So the pressure of the atmosphere, this. There was a pressure from the outside allowing some of the liquid to come out, but not all of the liquid. So when it came out, the average height of the mercury that remained inside the container, if you look right here, the height is around 760. And the measurement here is millimeters. So the chemical in here is called mercury. So this is called 760 millimeters of mercury. So if somebody asks, what's the atmospheric pressure? You can answer, the pressure of the atmosphere is 760 millimeters of mercury. Okay, so I was showing you the different conversions and the different units that are used to describe the pressure of mercury. So you know how the people who are announcing the weather, the weatherman, the weatherwoman, half the time I used to watch that when I was in Kansas. I lived in Kansas before, and the weather, oh my goodness, it would be a beautiful morning, 70 degrees. By afternoon, it's like 40 degrees. So I used to actually watch the weather every day. And they'll stand there, it's high pressure, it's low pressure, blah, blah, blah. They'll go into all this stuff. So I'm thinking, yeah, they have to measure the atmospheric pressure because I don't know that science. That's a whole different science. They know the changing in the atmosphere that causes the temperature to drop, the different weather tornadoes. And in Kansas, we had tornadoes, we had rain, we had all kinds of crazy stuff. Hail, a lot more hail than I've ever seen here in Texas. Yeah, there's a lot of hail there. There's a lot of weather stuff, I guess because of the location. So they'll tell you the pressure. And so based on this pressure, we're going to have rain. I'm like, okay, whatever you say. So I'll grab an umbrella with me to class. In the morning, it'll be beautiful. By the time I come out of class, it's raining, it's pouring, the weather is really bad. And they were able to tell all this by measuring the atmospheric pressure, right? So as we are learning about the pressure, we see the application outside of here. So as I was saying, they walk you through all of this here, the pressure and how the pressures relate to each other. So when I was giving you guys the conversions, I was essentially giving you the information that is on this table right here. It isn't really a table, but this slide right here. You have the atmospheric pressure in different units. So you will be given questions where you have to solve for the pressure in different units. Okay? So before I continue, I'm going to be setting up some questions for you to solve, and then we'll go back and forth. Before I continue, does anybody have any questions about the topic so far? So before I continue with this, let me give you a very, very brief overview because you'll be watching this on the video that's already recorded. But the first thing you'll be looking at is behavior of gas. The characteristic of gas is this. You want to ask yourself, when you're looking at a chemical, how do you know a chemical is a gas? Well, we know gases, right? Right now, for us to be alive, we are inhaling a gas. If you're not inhaling gas, if you're not inhaling air, you're not alive, right? So we have air all around us and we have experience with gases. But if you're in the lab, how do you know that you're dealing with a gas? We're told here gases can be compressed because if you look at the gas molecules, they're very far apart from each other. And we learned this before, right? In the first chapter, the second and the third chapters. Gases may also be expanded, so they can easily be compressed and you can easily expand them. Compressed means you're pushing the molecules closer, and expanded means you're pushing the molecules afar or yeah, far from each other. Gases have low density because between the gases there's just vacuum, there's nothing in there. I can't say there's air because air is a gas. Gas, as it says here, may be fixed in the volume. That means gas actually has the volume of container. Volume of container. So I'm not using my iPad for this part because this is not downloaded on the iPad. This is actually on my computer. So I'm using my mouse. Excuse my handwriting. This is the volume of container. Then we're told here gases can exert a constant pressure on the walls of the container. So for this part here, when the gas molecules are inside the container, they're stuck in there, right? So when they're in the container, they're stuck in there, they bounce in the container as they're moving around. So we see that when you have gas molecules inside the container, these molecules bounce on the walls of the container. And that's how we get the gas pressure. So what I'm going to do here is, since this is just the beginning of the chapter, once again, I'm briefly going over this. I'll let you guys have a chance to watch the video. Then I'll do a lot more conversions that are that have to do with the pressure of the gas, because understanding this definition right here is important. Okay. And so we'll go over conceptual questions on Thursday that have to do with the gas container. And if you guys have any more questions, once again, to do with chapter 2 or 3, bring that up on Thursday. If you don't have any questions about that, I'm going to be moving on to chapter 4. Okay. So as we look at this, the gases tend to have the volume of the container. They can also be mixed in the container. Gases tend to have a constant pressure based on them colliding with the wall of the container. Gases usually, they don't take up so much space even though they spread out. And so we'll talk about this some more down the road. Okay. As you guys read through all of these behaviors of gases, once again, come to me with questions. I want to set up a few questions so we can work on this that has to do with slide 16, where I started off right here. So for this, I'm going to navigate back to my slide that I had open. And I'm going to work out some few conversions that have to do with pressure. So for this one, without even going over the chapter, you should be able to perform this conversion here. I'll say we're going to convert 7.1 psi to atmosphere. Okay, we're doing simple conversions. So without really knowing the topic that much, you have the conversion factors right here, and I told you what they are. Oh, you have the conversion factors right here. Can you convert from 7.1 psi to atmosphere? I will set up my conversion brackets. 7.1 psi. As usual, look at the conversion list you have to pick from, right? Pick the one that has psi. So what conversion do I use that has psi in it?
The last one, 1 atmosphere equals
Okay.
14.7.
So you want to put the 14.7 psi on the bottom and then 1 atmosphere on top, right? So psi and psi cancel out. So you see, we're already using the same principle we learned in the previous chapter over here in our conversion, because every time we do conversion, we're doing dimensional analysis, right? So now I'll take 7.1 divided by 14.7, and that gives me 0.4829 ATM. But I want to round this up because this is two significant figures. So I'm going to round this up. This doesn't count. This remains. This remains. These drop off completely. So my answer will be 0.48 atmospheres, right? And then with these kind of questions here, they can mix it up so they can give you the ones that's two-step conversion. I'll just say the easiest for me, once I did a lot of these problems, was to realize in the conversion, they tend to give you a lot of atmosphere. You see the atmosphere here, the atmosphere here, here, and here. If they give you a two-step conversion, take it to atmosphere before you take it to the other unit. So I'll give you an example here. I'll say convert 100 kilopascals to, hold on a second, let me see what other units I have here. Actually, to psi. How about that? So go from 100 kilopascals to psi. So let me zoom out a little bit so you can see. So we're going to be using the conversion that has psi, right? So right here, we need the 1 atmosphere equal 14.7 psi. We need that conversion. We also need a conversion that has kilopascals in it. So I have the other one that's 101.325. Yeah, 325 kilopascals. This is equal to 1 atmosphere. So I go to my list I have here and I find the conversion that has kilopascals in it and the one that has psi, and I pull them to the side. So you see, essentially, we're going to be going not directly, but from kilopascals 2 atmospheres, from atmospheres to psi. So we're going to be doing 2 conversions. And that's how what we're doing in the previous chapter relates to this chapter. That's why we're practicing it there. Okay, let me set this up. 100. Oh, let me put a point here. So this is 3 significant figures. I'm making up these questions and I have to write kilopascals. Okay. So I picked the unit that has kilopascals in it. So it's going to be 101.325 kilopascals. The top one will be 1 atmosphere, right? And this cancels out. My next move, I'm trying to get to PSI through ATM. So right now I'm here. I have to get rid of ATM. I put 1 here. And then the top number is 14.7 PSI. So you see how it's not really that different? ATM, ATM, cancels out. And I have my answer in the desired unit. I have arrived at PSI. So for my mass, 100, remember this is 3 significant figures, dot, times 14.7. If you put a decimal there, that means those zeros are significant. Divided by 101.325. Okay? So 100 times 14.7 divided by 101.3. I get 14.507. This remains, this remains, this remains. Everything else gets canceled. 14.5 psi. That's my answer. Okay. So most of the questions are usually at this level right here. Let's see. Do you guys have any other questions from chapter 2 and 3? Because I know you haven't gone over this because you didn't even see the announcement I made. I have to send it out as an email. So you can watch the video before you show up, the old video, and then you have questions and it makes it easier. But do you have any questions about chapter 2, 3? Either homework or lab or vocabulary? Okay. If not, then what I can do next is I can continue going over this here. So since this is the first time that we're actually doing this, I did some math. Once again, feel free to go over the behavior of the gases right here. And I believe you'll go over that part. Another important concept we go over here is the kinetic molecular theory of gases. This is the theory that describes the characteristic of gases. So it summarizes all the behaviors that scientists know about gases in one neat space. Okay, give me just a moment. I heard something right here. Oh, okay. This isn't the conversion part, right? A per expression. Uh, the per expression is a conversion factor. Is the same thing. Man, they're hammering away outside. Let's see. Bring this up. So in your vocabulary, a per expression. Per in math means divided by. So it's kind of like miles per liter, something like that. So it's the same thing as a conversion factor. This is same as conversion factor used to convert from one unit to another. Okay? Yeah, because it's kind of the same thing. So you have per expression you have conversion factor, and you also have equality. Okay? Remember the table I had? I don't even know where it is right now. I have so many pages open, but the table is somewhere. Oh, there it is. This table right here, these tables, all these are technically equalities. They're not really conversion factors yet. But if you change them to per expressions, you can use them as a conversion factor, right? Like this one here, somebody was asking me about that. 1 milliliter equal 1 centimeter cube. If you write it like that, 1 milliliter equal 1 centimeter cube, that's an equality. This is an equality. And you can use that as 1 milliliter per centimeter cube. That's kind of like, 1 milliliter over centimeter cube. Conversion factor, you write it as 1 milliliter over 1 centimeter cube. And you use that to convert. It's technically equal to each other. Okay. So if you guys can think of any question, once again, just write it there, and then whatever I'm doing, I'll just stop and kind of address it and then move on from there. Okay. Okay. So I was looking, and of course, if there's no plan, then I'll just keep going on with the chapter 4 part, which I'm like, where's that page? Hold on, I see it. It's back there. I have so many pages open. Okay, right there. So yeah, the kinetic molecular theory, the questions tend to come from here, and they'll ask you behavior of gas. Is this behavior of gas listed in the kinetic molecular theory, or is it consistent? So of course you talk about a gas consists of molecules and empty space. When somebody tells you describe a gas, you're just talking about the particles in there, right? The molecules of the gas. Between the gas molecules, it's just empty. That's why you can compress a gas. The volume occupied by the molecules in the gas is negligible compared to the volume of the space they occupy. So what this is saying is if you have 1 gallon of gas, let's say this circle here is 1 gallon of gas, and you take all the tiny gas molecules together, right? And you squish them together because the gas molecules are so tiny. They didn't say that here, but it's implied. It's so tiny. If you try to figure out if this whole container is 1 gallon, and you try to figure out in that 1 gallon how much space is the actual molecules occupying, it's so tiny. So I'm going to put a tiny speck right there. Like that little dot compared to the whole gallon is where all your gas molecules are if you try to squish them together. If you take all the gas molecules and squish them together, compress them together to make one unit, you have them occupying this much space versus all the available space they spread out to. So the volume occupied by the actual gas molecules in the gas is negligible. It's almost like they don't even occupy any space when compared to the volume of the space they occupy. So the actual size they are very small compared to the space they spread out to. Okay? Now, if you let gas molecules go, they will spread out to all the available space. They will go to all the available little spaces in the container. But if you compress them, they'll take very little space. Attractive forces among gas molecules are negligible. We talked about this in the other chapter that the gas molecules don't really attract each other very much. They're there around each other, but they don't really attract each other that much. So one gas molecule is kind of freely moving away from another gas molecule without really attracting each other. Okay. And then we're told that the average kinetic energy of gas molecules is proportional to the temperature expressed in kelvins. That means kinetic energy has to do with moving, right? So the energy to move. Now we were told gas molecules have a lot of energy. Gas molecules are very energetic. And I used to joke with some of my students who were very energetic. I am considered energetic. I've been told I'm energetic. I have had no coffee. This is just, I had a good night. Okay, and I worked out last night, so I'm feeling extra energetic this morning. But I've been told I have extra energy, and I do have students who tend to have extra energy too. So I usually say, you know what, we are like gas molecules, constantly moving, high energy. So we're told here the kinetic energy of the gas molecules is proportional to the temperature. What does that mean? The temperature expressed in Kelvin. So we'll talk about this some more on Thursday. That means when the molecules are moving around, if you want them to move out even more or to move around even more to increase the motion, so if you want to increase motion of these gas molecules, in other words, you want to increase kinetic energy, just increase the temperature. Increase temperature. Why? Because it said right here, kinetic energy, the energy of the molecules, is proportional to the temperature. So if you increase temperature, you increase their energy and they move around a lot. You heat up a gas and the gas moves around a lot. And we're told here molecules will interact with one another and with a container without loss of energy. So if the gas molecules are moving and they happen to bump into each other, kind of like what's the game again with the stick and the balls? Not snooker. You guys don't call it snooker, not billiards. Pool. You know how the pool balls work? When the balls hit each other, sometimes one of them stops moving. But the way the molecules work here of gas, when one hits the other, they both keep going. They don't slow down for anything. So it says here when they bump into each other, when they interact, and with the container, they do not lose kinetic energy. They don't lose momentum. They don't slow down for each other. They keep going and they keep moving very fast. Okay? So, what we're going to do here when we get together later on Thursday, we'll talk about how the pressure of the gas is influenced by the collisions of the gas. So, I want to wrap this section here unless you guys have any other questions with this relationship here between gas pressure and number of collisions. So we were told earlier that the gas molecules are bumping into the wall of the container, right? They don't stay still. They're constantly moving around. When they bump into the wall of the container, the collisions of the particles create pressure. Because you're told here the force per unit area caused by collisions of particles with a container is essentially the gas pressure. Pressure is equal to force divided by area. Okay? So let me detour away from this slide so I can write over here. Because this is where I can write freely. So you have a container. I was trying to write there, but it was hard. And then you have molecules here. And every time the molecules collide with the wall, pressure is created. Okay? Every time the molecule collides with the wall, pressure is created. We have more pressure. So, if you have more molecules, you have more pressure, right? Because pressure is only created when the molecule bumps into the wall and it bounces off, and it bounces off like that. Okay? So, pressure of gas is created when molecules collide with the wall of the container. Okay? So let me ask you guys some questions. If that's the case, what do you think? So I'm going to write here, what will happen to pressure if? So I'm going to design some scenarios here. So I'm detouring away from the slides. And when we meet on Thursday, I remember we got to about slide, 13, 14, 16 right here. Okay. So I'll come back over that. But what will happen to pressure if number one, I increase number of molecules. So what I'm saying here is, for the same scenario, instead of having the three particles I drew here, I'm going to double it. Now I have 1, 2, 3, 4, 5, 6 colliding here, colliding here, colliding here, colliding here, colliding here, and colliding here. So I have increased molecules. What do you think will happen? I don't need this anymore. I can remove that. What do you guys think will happen if I increase the molecules of the gas? Oop, this helps if I can spell. Do I have more or less collisions?
There would be more.
Okay. Oh, now I can spell molecules. Since you have more molecules, this results in more collisions, right? So if you have more collisions, do we have more or less pressure? Says here, every time they collide with the wall of the container, that's when pressure is created. So we should have more pressure. Okay? So if you increase the molecules, more collisions, more pressure. So we can summarize. So summary, increase. Oh, let me write this from left so I can have enough space. Increasing molecules increases pressure. Okay, that's the first one. Second scenario that I'll change here is, I'll say, what if I decrease size of container? So for me to show you this, I'll show you two containers. One container with a big size to the left, one container that's really small to the right. I'm going back to my three amounts of gas. Three on the left, they're colliding here. Then I have three on the right, tiny molecules right here. So I have larger volume and I have less volume. What do you think will happen? So when I go to the right, like from left to right, if I decrease container size, what do you think this does to the collisions? Do I have more or less? What do y'all think? To the collisions. So at this point here, while you guys are thinking about it, I usually talk about this story that happened to me when I was in college. This is a true story. Usually my stories are true. But I used to run track back in the days. And sometimes it was very cold and we couldn't go work out outside because I said when I was in college, I started my first 2 years of college in Kansas. So my coach, if we couldn't go outside to run on the track because it was very cold, he wanted us to still run. We had to still stay conditioned. You know, it was part of what we did. So he would say, I want you, sometimes we'll run laps in the lab. I mean, sorry, not in the lab, sorry, in the gym. I spent a lot of time in the gym and in the lab. In the gym, we'll run laps like miles. Then sometimes he will have us run in the gym from wall to wall. Okay. So the gym was a big place. It had to accommodate different games in there. And he said, run all the way to one wall. And then when you get to the wall, tap the wall, like hit the wall. And I was like, okay, why is it important for us to hit the wall? I realized then that he wanted to make sure we run the whole distance. So you can't just kind of run halfway. if you're supposed to hit the wall. You have to run all the way to the wall, then hit it, then run back. And he said, do it fast. So of course people are running fast to the wall and then hitting the wall, running fast to the other wall and hitting the wall. Now I'm doing all this while I'm learning chemistry. So I'm doing all this, during the afternoon. In the morning I go to my chemistry class. So I'm trying to see the correlation between what I'm doing. And so I'm sitting there as I'm running back and forth. I'm so tired. I'm like, oh, can this gym be any smaller? I'm thinking about gas molecules. Once again, where I'm the gas molecule, this time the gym is a container. So I used to wish our gym was smaller so I didn't have to run so far. It took me so long because the gym was so big to get to the one wall just to hit it and then turn around again and then run all the way to the other wall, right? So when I think about this part here, it reminds me of being in school where I thought larger gym means it takes you longer to get to the walls, right? With a larger container, it takes the molecules a lot more time to get from one part to the other. When this molecule collides here, it has to travel far to get and collide here, right? But once this molecule collides here, it doesn't have to travel that far to collide again because the container is not that big. There's less space. So, that being the case, if you decrease the container size, do you have more or less collisions, or do you have zero difference? The molecules now have less distance to travel, right? And they're colliding and then moving around and colliding again and moving around and colliding again and then moving around and colliding again. I mean, yeah, colliding again, back and forth. What do you say? Decreasing the size, more or less collisions?
More.
Okay. More collisions, right? Because this is what I was hoping for. I was hoping our gym would just magically shrink. Because, yes, I'm the kind of person, I would do the workout, but I'll complain about it the whole time. I'm like, oh, this is so long. That's me. I have a trainer now, and I do the same thing. When I say hello to him and start complaining. What's the workout? Yeah. So more collisions. Yeah. So if you decrease the size of the container, you have more collisions, and you have increased pressure. And then let's see, what's the point? What else can I do? Pressure. Oh, this time I'll do the last thing and I'll let you guys go. It decrease temperature. We discuss increasing temperature, decrease temperature. So what if I don't change anything else? The size is the same, but all I do is make the container cold. Size is the same, molecules are the same, three, but somehow I decrease temperature. So what does the temperature do to the collisions? These molecules were moving very fast, right? Because they had a lot of energy, colliding with the wall, colliding with the container, colliding with each other, just all over the place. They have energy. As long as the temperature is high, they have energy. But now you go ahead and you decrease the temperature. So what does the temperature affect? I would say their energy, right? Now they're moving a little slower. They have the same distance to cover, but they're moving slower. So do you think they'll have more collisions or less collisions? I say here, less collisions. Why? Molecules move slower. That's like me when I have low energy. They move slower. So when they move slower, it takes them longer to get to the wall and take longer to get to the wall. Okay? They get there and they eventually collide with the wall, but it just takes longer because the temperature is lower. So it's like it's kind of like they skip their morning coffee. So they're dragging, but they're just doing it slower. Okay? So lower temperature, I'll just write here, lower temp results in less collisions. Ooh, it's like less collisions and therefore lower pressure. Okay, guys, that is it. That's all I have for today. It is 11 o'clock. I have my other class at 11:30. So yeah, please do watch the video. Let me make sure that the video is available for both classes. I'll post that. Watch at least the first half of the video. It's better if you watch both parts. It's only 30 slides, but that way when we meet on Thursday, we'll talk about any questions you have. If you don't have any questions, I'll come with my own set of questions that we can work on. That would be my plan B. My plan A is to answer your questions. And if you don't have a plan, then I'll always have a backup plan, which would be to work out problems. I'll go over the lecture part briefly, not like I did before, line by line, but just I'll kind of skim over the place, right? And then go over the questions that pertain to that point that I'm going over. Any questions? Okay, if you don't have any questions, guys, I will hopefully see you on Thursday. And this is going to be posted once it's done encoding. So if you don't see it, just ask me. And I'll call it chapter, since we discussed 2, 3, and 4, mostly 3 and 4, I'll call it chapter 3 and 4 discussions. Okay? Okay, y'all have a nice, it's not really afternoon yet, so have a nice day.
Bye. Thank you.
Uh, okay, bye.